today we will continue our discussion on invertible matrix. You remember last time we started the discussion on invertible matrices, and we gave uh, some equivalent criteria for when a matrix is invertible. And we proved that invertible matrices are those which are product of elementary matrices. All elementary matrices are invertible. Those are matrices corresponding to the three elementary row operations. Those matrices are invertible, and we proved that any invertible matrix is product of elementary matrices and vice versa. So in that sense, elementary matrices are the building blocks of all invertible matrices. Okay. We also proved a equational criterion for uh, invertible matrices. We showed that a square matrix A is invertible if and only if you look at the homogeneous system of linear equations. Then this has uh, only solution, only the zero solution if and only if A is invertible. Okay. And we also proved that if A times B equal to identity, then A is invertible, and B is the inverse of A. Okay. So we only need to check one condition, that A times B is identity, and the other condition B times A is equal to identity will be automatically satisfied. And we also looked at the row canonical form, that A is invertible. A is invertible if and only if the row canonical form of A is the identity matrix. Okay. So let us continue further discussion on invertible matrices. Right. So suppose we have a square matrix of size n by n, and there is a B, so that either BA is identity or AB is identity. Then A is invertible and A inverse is B. If A times B is invertible, then both A and B are invertible. Okay. So if B times A is identity, then I multiply this by the column vector X, and I get BAX is equal to X, because BA is identity. So if AX equal to 0, okay, if AX equal to 0, then by this equation, yeah, BAX is also 0, but BAX is X, and therefore X is equal to 0. So by the equational criterion for square matrices, a square matrix is invertible if and only if the homogeneous system AX equal to 0 has only trivial solution. Okay. So A is once BA is identity, then we have proved that A is invertible. And suppose C is its inverse. Suppose C is inverse. Then BA is identity. So C is equal to BA times C, and that is equal to B times AC. And C is the inverse of A. So AC is identity, and therefore BAC is equal to B. And therefore the inverse of A is actually this matrix B. Okay. So hence B is the inverse. And by similar technique, we can prove the other criteria. If AB is invertible and its inverse is D. Yeah. Is there a question? Somebody has a question? Yeah. So if AB is invertible, and suppose the inverse is D, then AB times D is equal to A times BD, and that is identity. And so A times BD is identity. So BD is the inverse of A. Okay. So if AB is invertible, then A is invertible. Similarly, we can prove that B is also invertible. Okay. So factors of an invertible matrix are invertible, and product of invertible matrices is also invertible. This we have proved before, because we proved that inverse of A times B is B inverse times A inverse. Okay. So suppose we have a square matrix which is invertible, and we want to solve a system of linear equations which is inhomogeneous, Ax equal to B. Okay. So if Ax equal to 0 and A inverse exists, that means x is equal to 0, because A inverse A x equal to Ix, and that is equal to x. Okay. So the homogeneous system for invertible matrix has only the 0 solution. So we look at the inhomogeneous system, Ax equal to B, where B is given. Now, in order to solve this system of linear equations, we look at the augmented matrix as we did before, AB, and then we know that the row canonical form of a invertible matrix is identity matrix. So by applying elementary row operations, this augmented matrix AB can be converted into IC, right? So by a sequence of elementary row operations, we convert A into I, and those elementary row operations will convert the vector B into C. Okay. So, so therefore, Ax equal to B if and only if Ix equal to C, because the system of linear equations which is given by this augmented matrix IC has same solution as the original system of linear equations. Applying elementary row operations does not change the set of solutions, but it changes the set of linear equations. So Ax equal to B if and only if X equal to C for X in R X a column vector, and therefore uh, X equal to C, right? Ix is X, so X equal to C, and therefore I substitute into X equal to B, and I get AC equal to B. Okay, so that gives an algorithm to find out solution of inhomogeneous equation using Gauss elimination method. Okay, you can say that uh, this why we need to do this, because if A is invertible, then we look at Ax equal to B multiply by A inverse, and that gives me Ix equal to A inverse B, and therefore X equal to A inverse B, right? X equal to A inverse B, but the problem is we have not found A inverse. Okay? And this Gauss elimination method, we will see later, it will calculate A inverse, but it also calculates the solutions. So we look at the augmented matrix AB by elementary row operations, convert A into identity matrix. Those elementary row operations will convert B into C, and then this C is the solution. Okay, because Ix equal to C, if you write down the system of equations corresponding to Ix equal to C, it is just saying that x1 equal to C1, x2 equal to C2, and xn equal to Cn, and therefore x equal to C, right? So therefore, C becomes the solution of the inhomogeneous system of linear equations. Okay, and it is a unique solution, right? So this observation is the basis of important method to find the inverse of a square matrix. And this is called the Gauss-Jordan method of inverse of a matrix. You might have learned in school that inverse of a matrix can be found by using cofactors and determinants, etc., etc. That those formulas are useful to some extent. They are computationally very heavy. I will discuss those formulas also. But an efficient method to calculate inverse of a matrix is the Gauss-Jordan method, which is dependent on what we just observed. That if we have invertible matrix, Ax equal to B, then a solution can be found by converting A into row canonical form, and those elementary row operations will convert the vector B into a vector C, and that C is the solution. So let us use this fact to understand the Gauss-Jordan method to find inverse. So let's consider an invertible matrix. Yeah? Uh, and suppose C1, Cn are unique elements so that AC1 is E1. Yeah. So we just proved that if I look at the equation AX equal to E1, then there exists a unique C1 such that AC1 equal to E1. Okay. So similarly, we find unique C2 so that AC2 is equal to E2, and unique Cn so that ACn is En. Yeah, we solve this n system of linear equations, inhomogeneous linear equations. Okay, by converting A into the row canonical form. Okay, we can do this solving these n equations in n unknowns, n systems of n equations in n unknowns simultaneously by constructing a matrix C. Yeah. So we want to find this matrix C whose column vectors are C1 to Cn, so that AC1 is E1, ACn is En. But you see, A times C is can be multiplied like this. Display the column vectors of C, then the column vectors of AC are AC1, AC2, and ACn, right? But AC1 is E1, AC2 is E2, and ACn is En. So A times C is this matrix, which is identity matrix, and therefore C is the inverse. Yeah. So once I get AC equal to identity, then C is inverse. So what are we doing? We are simultaneously solving these n system of linear equations in n unknowns, and the right hand vectors are E1, E2, En, and this we do simultaneously. So this, by last corollary, it follows that this matrix C that we find by solving these systems of equations is the inverse of A. Okay, so to find A inverse, we solve these system of equations: AX1 equal to E1, AX2 equal to E2, AXn equal to En, and we can do this simultaneously by making a big augmented matrix. Yeah. So if we have one system of linear equations, I just add the vector B and make a augmented matrix. But now we are solving n systems of linear equations. So I make this E1, E2, En, and this bigger augmented matrix, which has n rows and 2n columns. And this we write notation AI. I is the identity matrix. Okay, and now we transform. So this n by 2n matrix is there. We apply row operations, elementary row operations, to convert this n by 2n matrix into row canonical form. And since A is invertible, the row canonical form of A will be identity. Okay, so AI is transformed into identity, and then this matrix identity matrix is transformed into C. Okay, and this C is the inverse. Right? So it is saying that if I want to find inverse of a matrix, then just put identity matrix and make this n by n by 2n matrix and do elementary row operations until we reach identity matrix here. Then this matrix get transformed into A inverse. Yeah, is that clear? Any doubts? So this is the algorithm to find Gauss-Jordan algorithm to find inverse of a matrix. Okay. So to carry out the above process, we need not know beforehand that the matrix is invertible. So we showed last time that if I am given a n by n matrix, to test whether it is invertible, we just try to find its row canonical form. And we proved that the matrix is invertible if and only if the row canonical form is identity matrix. So we just set up the equations ax1 equal to e1, ax2 equal to e2, etc., and apply Gauss-Jordan process. At the end, suppose the row canonical form of A doesn't turn out to be identity matrix, then it says that the matrix is not invertible. Okay, says the matrix is not invertible, and therefore, in this case, ax equal to 0 will have infinitely many solutions. Okay, so so this process itself reveals that whether A is invertible or not. So let's look at an example. Look at this 3 by 3 matrix. Okay, look at this 3 by 3 matrix. It's not clear whether this is invertible or not right now. Okay, so this is a coefficient matrix of a system of linear equations in 3 unknowns, and there are 3 equations. Okay, so use elementary row operations to transform the augmented matrix. This is a 3 by 6 matrix. Yeah, they convert this into. We will try to convert this into row canonical form, which may or may not be identity, and then this identity matrix is transformed into the matrix C, and that is likely to be the inverse if A is invertible. Okay, so we have gone through this process. Convert this. This is the identity. We juxtapose identity matrix with the original matrix, and then try to convert this 3 by 6 matrix into a row canonical form. And we find that this is the row echelon form. Yeah, this is row echelon form. But now we have to go into Gauss-Jordan method, and starting from -5, we have to convert these into zeros. Then we convert this into 0. But before that, these pivots, these 3 pivots, have to be converted into ones. So at this point, it is clear that the original matrix is invertible. Yeah, the original matrix is invertible, because what has happened is original matrix was A, and then we applied some elementary row operations, E1, E2, ER, and then this becomes this matrix U. Okay, this matrix U is upper triangular matrix, and the diagonal entries are non-zero. And we showed that if I have a system of linear equations whose coefficient matrix is upper triangular and diagonal entries are non-zero, it has a unique solution. Okay, it has unique solution. So therefore, this matrix A must be invertible. And now we convert this into the row canonical form, yeah, by elementary row operations, and this is what we end up with. So the original identity matrix, this identity matrix by these elementary row operations is converted into this. This matrix A is converted into identity matrix. So A is invertible, and this is the inverse. This is the A inverse. Okay, and we can simplify convert the decimals into fractions, and A inverse is 1/10 and times this 3 by 3 matrix. It is one of the most efficient methods to find inverse of a matrix, or solve a system of inhomogeneous equations, Ax equal to B, where the matrix is invertible.